When we have things that are small and too numerous to count efficiently, we sometimes count them by weighing them. You go to the hardware store and maybe you're building a garage and you go in there and you say, I need 2,500 nails. Is the guy going to stand there and count out 2,500 nails? No. They're going to figure out how much that many nails weighs, and then they're going to give those to you by weighing. So we can count things by weighing. We still need to know the relationship of the number of nails to how much they weigh. So here's an example. And I'm going to try something here. Let's see if this works. No, I don't think it's going to work. I won't try it. Never mind. So a hardware store customer buys 2.60 pounds of nails. A dozen of the nails weigh 0.150 pounds. How many nails did he buy? Okay, this goes back to chapter 2. This is dimensional analysis, just working with units. So there's a hidden conversion factor in here. 2.60 pounds of nails is our starting, and a dozen nails weighs 0.50 pounds. That's our hidden conversion factor. So a dozen nails is 0.150 pounds, and then we know that 12 nails equals a dozen. So we can start with pounds of nails and convert to dozens of nails by knowing how many pounds a dozen weighs, and then knowing the number of nails in a dozen, we can convert to number of nails. So here we are with 2.60 pounds. We're going to multiply by dozen and divide by pounds, and the pounds cancel out, and then we're going to multiply by 12 nails per dozen, and we're going to end up with a total of 208 nails. Does that make sense? Yes? One person nodded their head, so we'll go with that. So let's go over that one more time. Okay? We've got, what was it, 2.60 pounds? 2.60 pounds of nails. And we were told that a dozen nails weighed 0.150 pounds. That was hidden in the words of the question. So that allows us to figure out from the mass, the weight, how many dozen nails we have. And then we know that there are 12 nails in every dozen nails. And then we multiply and divide, and we come up with 208 nails. Okay? This chapter is where we really start applying the things we learned in chapter 2 about dimensional analysis. With atoms, we have to use their mass as a way to count them because they're way too small. And they're too numerous also. This is a great little blurb here. Even if you could see atoms and counted them 24 hours a day as long as you lived, you would barely begin to count the number of atoms in something as small as a grain of sand. So if you counted atoms for the rest of your life, 24/7, didn't take a nap, didn't eat, didn't do anything else but count atoms, you couldn't even count the atoms in one grain of sand. We can't count atoms. It's ridiculous. So we weigh them instead. Just like we can count nails by weighing them, we know how many nails are in a certain mass, and then we weigh them, and then we can figure out the number of them. We do the same thing with atoms. So dozen worked with nails, but it's way too small to use with atoms. So we need a bigger number. So we have what sometimes is referred to as the chemist's dozen. It's a little bigger than 12. It's 6.022 times 10 to the 23rd. So we all understand that a dozen is 12 items. It could be 12 donuts, it could be 12 bagels, it could be 12 planets. You know, it could be anything. A dozen is 12. A mole is 6.022 times 10 to the 23rd things. That's all it is. Could be anything, okay? You need to know that number. And we'll use it a bunch, 6.022 times 10 to the 23rd. So I'll just tell you a little story here. My, let's see, which one is he? My fourth son was born on October 23rd. And he weighed 10 pounds. And he was 23.5 inches long. See a correlation of numbers there, 10 to the 23rd. My husband's a chemist, I'm a chemist. Chemists celebrate Mole Day on October 23rd because it's 10/23. Have you heard of Pi Day? Mathematicians. Pi Day. Pi is 3.14159 on forever. They celebrate that on March 14th. So chemists celebrate Mole Day on October 23rd. So we had a child who was born on Mole Day, and not only that, but he weighed 10 pounds and was 23 inches long. We, I did my best to have him at 6:02 a.m. or p.m. It didn't work out. It was more like 8:30. But, close enough. So he's our mole baby. So 1 mole of anything is that number. And the number has a name. It's called Avogadro's number, named after Amadeo Avogadro, whose work led to us figuring out what that number was. So a mole of marbles, 6.022 times 10 to the 23rd marbles. A mole of sand grains, 6.022 times 10 to the 23rd sand grains. It's good to have an idea of roughly how big these things are. So if you had a mole of copper atoms, here's a picture. This is how much copper would contain 6.022 times 10 to the 23rd copper atoms. It'd be 22 copper pennies. That's about 1 mole of copper. Over here, 2 large helium balloons. That's approximately 1 mole of helium atoms. Now those are going to occupy a larger volume because helium's a gas and there's a lot of empty space between the atoms. But so a mole of atoms is an amount that you can see and hold. It's not so big that it's, bigger than the building, but it's not so tiny that you can't see it either. So it's a very useful amount. It's reasonable. Like a dozen nails is a reasonable number of nails. Okay? All units are man-made, obviously. There's no real intrinsic unit. And some of them were created with more thought than others. Do you know where the unit of foot came from? It used to be the length of the ruler's foot. The king or whoever it was, that however long his foot was, that was a foot. And since, most grown people's feet are roughly the same, it was an okay approximation, but it was related to your foot. In chemistry, these units, like mole and atomic mass unit, have been carefully thought out so that they work together very nicely. So this definition is going to seem a little crazy. The mole is the number of atoms in exactly 12 grams of pure carbon-12. Okay, right? What does that mean? Well, the atomic mass unit was 1/12 the mass of a carbon-12 unit. And so because of this, there's a relationship between moles, atomic mass units, and grams. And what it is that when we look at the atomic mass, let's say look at carbon. On the periodic table under carbon, it says 12.011. It doesn't say exactly 12 because that's the average of all the different isotopes. But an average carbon atom would weigh 12.011 atomic mass units. A mole of carbon atoms is going to weigh 12.011 grams. So those numbers give us the mass in atomic mass units of one atom, or the mass in grams of a whole mole of atoms. Okay, and that allows us to count atoms by weighing them, because we know in 12.011 grams of carbon, the average mixture of carbon that we have, there's going to be Avogadro's number of particles, of atoms. So we use this as a conversion factor. So 1 mole equals 6.022 times 10 to the 23rd atoms. This is a conversion factor. So we can do problems like this. Convert 7.2 moles of neon to number of neon atoms. So we're going from moles to atoms. The word mole is a very short word, M-O-L-E. It's only 4 letters, and yet it has an abbreviation, M-O-L. Personally, I think they should use that for the word molecule. I think we could all just draw the extra E on mole, but no. If you have molecules, you have to write out the whole long word. If you're using moles, you can abbreviate it MOL. Doesn't make sense to me, but that's what it is. The relationship between moles and atoms is Avogadro's number. And so we just go 7.2 moles times, get some more room here, and we're going to have moles on the bottom and atoms on the top. And that's dimensional analysis, chapter 2. These moles cancel out. Students sometimes get confused and put the 6.022 times 10 to the 23rd on the wrong side of the line. So remember, it's like a dozen. Are there 12 dozen in one egg? No. 12 eggs is 1 dozen. Mole is like dozen. The number doesn't go with that. It goes with the objects. So 6.022 times 10 to the 23rd. If you have not figured out how to use scientific notation on your calculator, now is the time where you really, really have to, because you can't put that number in without using the EE button or EXP button. So make sure that you know how to use your calculator. 7.2 times 6.022 EE23 equals. And I didn't really leave myself very much room there. I'm going to write it down below. So this number should have 2 significant figures because our initial number was 7.2. So I'm going to round this to 4.3 times 10 to the 24 atoms. When you're solving for a number of particles, whether it's atoms, molecules, ions, you're never going to end up with a negative exponent. If you had a negative exponent because you put the number in the wrong place or you divided instead of multiplying, that would mean you have less than 1 atom. You can't have less than 1 atom. Atoms are the smallest building blocks. You can't have part of an atom, okay? It's like you'd figure out how many people there were in attendance at a concert, and you find out it's 0.75 people came. Is that possible? It's not possible. Okay? So none of these problems will give you less than 1 atom. So that exponent's always going to be positive. Any questions about that one? We can do it the other way around. We can convert from number of atoms to moles. So here's platinum atoms. Does it really matter that it's platinum atoms? No, it doesn't, because a mole refers to anything. So here we're going to start with 5.2 times 10 to the 25 atoms. You just really need to write your units on everything. Times, atoms go on the bottom, and moles go on the top. 1 mole is Avogadro's number of atoms. It's really small. So we've got 5.2 EE25 divided by 6.022 EE23. And this should also, thank you computer, wake up. This should also have 2 significant figures because our initial number had 2. So this is going to end up to be 86 moles. Any questions? You got 8.6? So, just like nails, let's think about the nails again. And while I'm talking, look and see if you can figure out what's wrong with this picture. So if we had a dozen large nails and a dozen small nails, would they weigh the same amount? Would they? No. Have you figured out what's wrong with the picture? How many small nails are there? There's only 11. Why do I notice these things? I do not know. But, you know, it's just really, can't you do that correctly? So I'm going to fix it. There. Now there's 12 nails. Good grief. But a dozen large nails are going to weigh more than a dozen small nails, right? Because each individual big nail weighs more than the little one. We have the same number of each of them, right? So the big ones have to weigh more. Well, atoms don't all have the same mass either. So here we have 2 pictures. This is a mole of sulfur atoms. A mole of sulfur atoms weighs 32 grams. And here's a mole of carbon. Kind of looks like graphite. And that weighs 12 grams. So a mole is, these are the same number of atoms. On each little watch glass there are 6.022 times 10 to the 23rd atoms of that element. Why does the sulfur weigh more? Because each atom weighs more. If you look at the periodic table, the average mass of a carbon atom is 12.011 atomic mass units, and the average mass of a sulfur atom is 32.07 atomic mass units. So a mole of sulfur weighs more because each atom weighs more. So we mentioned atomic mass units before. It's defined as 1/12 of the mass of a carbon-12 atom. And we learned how to find the mass of a formula by adding those numbers up. Now we're going to introduce a very similar idea, the molar mass. The atomic mass is the mass of an atom. The molar mass is the mass of a mole of particles. What's nice and convenient is that the molar mass in grams is the same number as the atomic mass in atomic mass units. So on the periodic table, carbon, not carbon, that's copper. A copper atom has, on average, a mass of 63.55 atomic mass units. If we have a chemist's dozen of those, a mole of them, a mole of copper atoms, 63.55 grams. So 1 mole weighs 63.55 grams. So we say that the molar mass is 63.55 grams per mole. So every mole weighs that many grams. That looks like a conversion factor, doesn't it? And it is. It's a really useful one. So the mass of a mole is different for different elements. For sulfur, a mole is 32 grams, but it's still Avogadro's number of particles. For carbon, Avogadro's number of particles equals 1 mole, but the carbon weighs 12 grams, because that's like the smaller nails. Each carbon atom weighs less, and so that giant dozen of them weighs less as well. Lithium is even smaller. A mole, though, is still 6.022 times 10 to the 23rd lithium atoms. But these weigh only 6.94 grams. But each of these lines is a conversion factor. You can say that 6.94 grams of lithium equals 1 mole. You can say that 1 mole equals Avogadro's number. You can also say that Avogadro's number of lithium atoms is going to weigh 6.94 grams. So there's actually 3 conversion factors in one right there. But molar mass is the conversion factor between grams and moles. And that's just a real important thing to recognize. We're going to use molar mass a lot. Because weighing is how we can measure things. We can't count the atoms, and yet when we look at chemical reactions, they happen between particles, and so we have to deal with numbers of atoms. And so we need to use moles and we need to use grams, and this is how we get between them. So let's do an example. Calculate the number of moles of calcium in 91.4 grams of calcium. So we're given a mass of calcium, 91. That's not going to work. 91.4 grams of calcium. And we're asked to convert to moles of calcium. We can go directly from grams to moles using molar mass. So what is the mass of 1 mole of calcium? We have to look at the periodic table. We look at the periodic table and we see that 1 mole of calcium equals 40.08 grams of calcium. So we have our path of grams of calcium to moles of calcium. We have our relationship there, and so now we can go ahead and do the equation. 91.4 grams of calcium times, we want moles on the top and grams on the bottom. Grams of calcium and moles of calcium. 1 mole weighs 40.08 grams. And we take our calculator, 91.4 divided by 40.08. How many significant figures should our answer have? 3, because our initial number has 3. So this is going to come out to be 2.28, and the unit is moles of calcium. So this is dimensional analysis. We've just got a new conversion factor. Going between grams and moles or moles and grams for any element, the conversion number that you need is on the periodic table. On an exam, you will always have a periodic table with you. One of the first things I did when I got my smartphone was to download a periodic table for my phone. Because you just never know when you're going to need to know the mass of zirconium, you know. That was supposed to be funny, and no, it wasn't. Yeah. Calculate the mass of aluminum, grams, in 6.73 moles of aluminum. So there's only one number in this problem, so that must be where we start. 6.73 moles of aluminum, and they're asking for grams of aluminum. Well, what's the relationship? Look in the periodic table. Under aluminum, it says 26.98. 26.98. That means that many grams of aluminum is how much 1 mole weighs. So then we write 6.73 moles. And get in the habit of including the element symbol there. It'll be really helpful later. Then we're going to have grams of aluminum and moles of aluminum These moles are going to cancel out. It's always 1 mole and 26.98 grams. Because, if you go buy donuts, how do they price them? They price them either per donut or per dozen donuts. They don't go in and, you don't go in there and on the sign it says, well, for $5 you can get 1.27 dozen donuts. Right? They don't do that. 1 dozen is how much? So the mole is the chemist dozen. 1 dozen, 1 chemist dozen of atoms weighs how much? It's not the other way around. 6.73 times 26.98. Calculator malfunction. Or maybe it's user error. How many significant figures should our answer have there? 3. Equals, so I get 182 grams of aluminum. Anybody else get that? Yesterday in my other class I kept making mistakes, and they caught me, which was good. Any questions? So we can also use those relationships to go between number of atoms and grams. So just like we did with the nails, we had so many pounds of nails, and we figured out it was 208 nails. We could also take a mass of aluminum, say, and find out how many atoms are in there. This isn't the sort of problem that we do as often as grams and moles, but we need to know how to do it. So here we've got, we're given 16.2 grams of aluminum. And they're asking how many aluminum atoms are there. So we want to go from grams to atoms. Well, we're going to need the molar mass off the periodic table. Again, that's 26.98. 26.98 grams of aluminum equals 1 mole of aluminum. But what does 1 mole equal? 6.022 times 10 to the 23rd atoms. We could do this as a 2-step conversion and go from grams to moles to atoms, or we could do it in 1 step. I think 1 step's better. So I'm going to show you how to do it in 1 step. 6.2 grams, 16.2 grams of aluminum. We want to multiply by atoms and divide by grams. Look at this here. This many grams of aluminum is 1 mole, but 1 mole is this many number of atoms, this number of atoms. So we could say that 26.98 grams of aluminum is 6.022 times 10 to the 23rd atoms. Just like if it was $5 for 1 dozen donuts, you could also say it's $5 for 12 donuts, right? A dozen and 12 are exactly the same amount. So that's what we're going to do here. So atoms is 6.022 times 10 to the 23rd. And that many atoms is 1 mole, which weighs 26.98 if those are aluminum atoms. 16.2 times 6.022 raised to the 23rd power divided by 26.98. And again, we're going to end up with 3 significant figures. Do we expect, this is an aluminum can, do we expect the number of atoms to be a really big number or a really small number? It's a really big number. This is an object that's large enough we can see. It would take us an entire lifetime and more to count the atoms in a grain of sand. The aluminum can has more atoms than a grain of sand. This is going to be a big number. 3 significant figures, and so my calculator is giving me 3.615, which I'm going to round up to 3.62 times 10 to the 23rd atoms of aluminum. Anybody else get that number? Always a good idea to do this twice. I don't do it in lecture because you're already, sitting there while I punch numbers in my calculator. But do it twice. If you come up with the same answer, it's most likely correct, or you're just really good at making mistakes consistently. If you come up with 2 answers that are different, then go for best 2 out of 3.